Section: Introduction. In this section, we introduce the significance of large language models, like those from OpenAI, which excel in reasoning and inference. We recognize that vision is equally crucial for models to comprehend the world fully. Thus, we aim to develop a multimodal model that combines language and vision to enhance reasoning capabilities. We note that early vision language models primarily provided direct answers to questions, which limited their effectiveness in tasks requiring logical reasoning due to a lack of structured thought processes. Recent research indicates that using chain-of-thought reasoning can improve question answering by encouraging step-by-step reasoning. However, we find that many existing models still produce errors or misleading outputs because their reasoning processes are not sufficiently systematic or structured. By systematic, we mean that the model should engage in multistage reasoning rather than just a direct response. Structured refers to the model's ability to clearly identify and understand the reasoning stages and tasks at each step. We observe that many models start answering without properly organizing the problem or the information available, often jumping to conclusions prematurely. To address these issues, we have designed LLaVA-o1, which allows for independent systematic and structured reasoning. While some initial explorations into OpenAI's models exist, many technical details remain unclear. Our work aims to enhance a model's ability to reason autonomously through supervised fine-tuning. LLaVA-o1 generates responses in 4 distinct stages: summary, caption, reasoning, and conclusion. Each stage serves a specific role in the reasoning process. We also implement dedicated tags to mark the beginning and end of each stage, which helps maintain clarity throughout the reasoning. Unlike traditional chain-of-thought reasoning, our approach promotes structured thinking by first organizing the problem and known information, then conducting a detailed analysis, and finally deriving a conclusion. We create the LLaVA-o1 to 100K dataset by generating responses stage by stage and train the model using supervised fine-tuning. Our structured reasoning approach also enhances inference time scaling. Instead of conventional methods, we use a novel stage-level beam search that generates multiple candidate results at each stage, selecting the best one to continue the process. We conduct experiments on various multimodal reasoning benchmarks and find that LLaVA-o1 significantly outperforms traditional chain-of-thought prompting, especially in complex tasks. In summary, we present LLaVA-o1 as a visual language model designed for systematic reasoning, demonstrating exceptional performance in structured thinking tasks. Our stage-level beam search method is scalable, allowing for improved performance with increased computational resources. Extensive experiments show that our approach outperforms larger, closed-source models, highlighting the effectiveness of LLaVA-o1 for multimodal reasoning. Section Summary. In this section, we introduce LLaVA-o1, a multimodal model that enhances systematic and structured reasoning by generating responses in 4 distinct stages: summary, caption, reasoning, and conclusion. Our approach, which employs a novel stage-level beam search method, significantly improves performance on complex reasoning tasks compared to traditional chain-of-thought prompting, demonstrating the model's effectiveness in multimodal reasoning scenarios. Section: Visual Reasoning with Large Language Models. In this section, we discuss visual reasoning with large language models, LLMs. Visual reasoning requires both visual perception and advanced cognitive skills. We evaluate the visual reasoning abilities of vision language models, VLMs, through tasks like visual question answering, VQA, where models answer questions based on visual content, and visual entailment, which checks if text descriptions match visual information. Traditional VLMs use neural symbolic methods to model visual reasoning explicitly. However, with the rise of LLMs, VLMs now utilize their advanced reasoning skills for visual tasks. Some models improve visual reasoning by refining how they encode visual information, creating tokens that focus on cognition. For instance, VISPROG uses the LLM as a decision maker, enhancing reasoning in complex visual tasks by integrating various specialized visual modules. Additionally, techniques like prompt tuning and supervised fine-tuning help boost visual reasoning capabilities. Next, we explore chain of thought, COT, prompting, which provides a step-by-step reasoning process for LLMs when tackling difficult questions, including those requiring common sense or logical reasoning. COT prompting breaks down questions into smaller reasoning steps, guiding the model to solve complex problems incrementally. Recent studies show that COT prompting significantly enhances both reasoning and interpretability in LLMs. We also examine inference time scaling methods, which fall into two categories: those using an external verifier and those that do not. External verifier methods are common, while independent methods include majority voting, best-of-n search, and sentence-level beam search. Majority voting works well for problems with standard answers but is less effective for open-ended tasks. Best-of-n search generates multiple complete answers for selection, but this can complicate accuracy evaluation. Sentence-level beam search creates several candidate sentences and selects the best, but it can be too detailed for effective quality assessment. Our proposed method, LLaVA-o1, supports a progressive reasoning process that enhances VLM's reasoning abilities and improves inference time scaling. By employing structured thinking, LLaVA-o1 achieves a systematic reasoning process and excels in scalability compared to existing methods. This design ensures robustness and accuracy in complex reasoning tasks, distinguishing it from traditional approaches. We aim to train a visual language model capable of extended reasoning chains for systematic and in-depth analysis. LLaVA-o1 breaks down the answer generation into 4 structured stages. 1. Summary stage. Here, LLaVA-o1 provides a high-level summary of the question, highlighting key aspects. 2. Caption stage. If an image is involved, LLaVA-o1 gives a brief overview of relevant visual elements to aid understanding. 3. Reasoning stage. Building on the summary, LLaVA-o1 conducts logical reasoning to formulate a preliminary answer. 4. Conclusion stage. Finally, LLaVA-o1 synthesizes the answer based on previous reasoning, adapting the output to user needs, whether concise or detailed. Each stage is initiated at the model's discretion, using special tags to guide the process. The model autonomously selects these tags and activates stages based on its judgment, completing all stages in a single inference pass. This structured approach allows the model to manage its reasoning independently, enhancing its adaptability and performance in complex tasks. Section Summary. In this section, we discuss our proposed model, LLaVA-o1, which enhances visual reasoning in vision language models, VLMs, through a structured, 4-stage reasoning process that includes summarizing, captioning, reasoning, and concluding. This systematic approach allows the model to autonomously manage its reasoning, improving its performance and adaptability in complex tasks without relying on external prompts. Section: Data Preparation and Model Training. In this section, we discuss our data preparation and model training process. We noticed that most existing visual question answering (VQA) datasets do not provide the detailed reasoning needed for training our LLaVA-o1 model. To address this, we created a new dataset by combining samples from various popular VQA datasets, resulting in 99,000 image question-answer pairs, which may include multiple rounds of questions. Since there is currently no multimodal model that can generate structured reasoning directly, we utilized GPT-4o to create detailed reasoning processes, including summaries, captions, reasoning, and conclusions. This information was compiled into the LLaVA-o1 to 100K dataset, which we plan to make publicly available. Our dataset includes both general-purpose and science-focused VQA datasets. For general-purpose datasets, we incorporated shared GPT-4 volts for multi-turn question answering, ChartQA for interpreting charts, AOKVK for external knowledge, DOC-VQA for document-based questions, PISC for social relationships, and CLEVR for object properties and counting tasks. For science-focused datasets, we included GeoQA+ for geometric reasoning, AI2D and Science QA for scientific questions, and CLEVR Math for arithmetic analysis in visual contexts. We then used the LLaVA-o1 to 100K dataset to perform supervised fine-tuning, SFT, on the LLaMA 3.2 to 11B Vision Instruct model, conducting full parameter fine-tuning on a single node with 8H100 GPS. To improve the model's reasoning ability during inference, we implemented a stage-level beam search method. This involves sampling responses at each stage, selecting the best ones, and repeating the process until all stages are completed. The structured output design of LLaVA-o1 allows for efficient verification at each stage, enhancing inference time scaling. We also compared the performance of LLaVA-o1 with the base model on 6 widely used multimodal benchmarks to demonstrate the effectiveness of our training approach. We conducted ablation studies to answer 3 key questions: whether our LLaVA-o1 to 100K dataset is more effective than the original dataset, the impact of structured tags on performance, and the specific areas where our model shows improvement. For our experiments, we selected 6 challenging benchmarks: MM*, MM-Bench v1.1, MM-Vet, Math Vista, AI2D, and Hallusion Bench. We ensured fairness and reproducibility by using VLM EvalKit, an open-source evaluation toolkit for large vision language models, to derive performance metrics for all baseline models. Section Summary. In this section, we compile a new dataset, LLaVA-o1 to 100K, consisting of 99K image QA pairs from various VQA datasets, and utilize GPT-4o to generate detailed reasoning processes for training the LLaVA-o1 model. We also implement a structured output design to enhance inference time scaling and evaluate our model's performance against 6 multimodal benchmarks, demonstrating significant improvements in reasoning capabilities. Section: Benchmark Results. In this section, we present our benchmark results. We found that LLaVA-o1 shows significant performance improvements, even with just 100,000 data points. Compared to the base model, LLaMA 3.2 to 11B Vision Instruct, LLaVA-o1 excels in various tasks, including general visual question answering, mathematical reasoning, scientific visual question answering, and controlling hallucinations, achieving an average score increase of 6.9%. This confirms the effectiveness of our approach. Next, we conducted an ablation study to compare LLaVA-o1 to 100K with the original datasets. Our findings indicate that while the model trained on original question and answer pairs shows some improvement, its overall performance is still significantly lower than LLaVA-o1. Notably, on the MM-Vet benchmark, which demands detailed responses, it performs worse than the base model. This highlights the importance of our multistage LLaVA-o1 to 100K dataset for training models that can handle advanced reasoning. We also examined the role of structured tags in enhancing performance. By comparing LLaVA-o1 with a version that had the structured tags removed, we observed a significant drop in performance without the tags. This suggests that structured tagging is crucial for facilitating reasoning and improving model performance. To our knowledge, LLaVA-o1 is the first model to successfully enhance reasoning abilities through structured reasoning with tags. We analyzed the specific areas where LLaVA-o1 improved compared to the base model using the MM* benchmark, which assesses 6 key skills: coarse perception, fine-grained perception, instance reasoning, logical reasoning, math, and science and technology. Our analysis shows that LLaVA-o1 excels in systematic reasoning tasks, such as instance reasoning and logical reasoning, while showing smaller gains in perception tasks. This indicates that our method primarily enhances reasoning capabilities. In terms of inference time scaling, we compared our stage-level beam search approach with traditional methods like best of n and sentence-level beam search under similar computational conditions. We evaluated across the same 6 benchmarks to ensure consistency. Our results demonstrate that stage-level beam search effectively utilizes the structured reasoning stages of LLaVA-o1, achieving higher accuracy in complex reasoning tasks without significant computational costs. When comparing our method to baseline inference scaling methods on the MMVet benchmark, we ensured a fair evaluation by using similar inference time computations. Our stage-level beam search improved performance by 2.6%, while the best of N method only showed a modest improvement of 0.6%, and the sentence-level beam search even decreased performance by 1.9%. We found that the sentence-level approach struggled with open-ended questions due to its overly detailed nature. Finally, we explored the scaling trend of our stage-level beam search by testing LLaVA-o1 with different beam sizes on the MMVet benchmark. We generated 1 to 4 candidate responses at each reasoning stage, allowing the model to choose the best answer. Our results confirmed that as the number of candidate responses increased, the model's performance improved consistently, indicating that our stage-level beam search is scalable. Although we only tested a beam size of 2 across all benchmarks due to resource constraints, we anticipate that larger beam sizes would yield even greater improvements. Section Summary. In this section, we demonstrate that LLaVA-o1 significantly enhances performance in various reasoning tasks, achieving an average benchmark score increase of 6.9% despite using only 100K data. Our findings also highlight the critical role of structured tags and the effectiveness of our stage-level beam search approach in improving inference accuracy and scalability in complex reasoning tasks. Section: Comparison to state-of-the-art VLMs. In this section, we compare LLaVA-o1 with other leading vision language models, both open source and closed source, across 6 benchmarks that require advanced reasoning skills: MMStar-R, MMBench-R, MMVet-R, MathVista, AI2D, and HallusionBench. We derived MMStar-R, MMBench-R, and MMVet-R from their respective original benchmarks, removing tasks that only needed basic perception or optical character recognition, so we focused on those that require complex reasoning. For MathVista, AI2D, and HallusionBench, we included all tasks since they are designed for advanced reasoning. Our findings indicate that LLaVA-o1 consistently outperforms many open-source models of similar or larger sizes, such as Intern VL2-8B and Ovis 1.5 Gemma 2-9B, as well as some closed-source models like GPT-4o Mini and GEMINI 1.5 Pro. This highlights the effectiveness of our structured reasoning approach and positions LLaVA-o1 as a strong contender in reasoning-intensive vision language model tasks.